Okay, welcome. My name is Ryan Hoger with Temperature Equipment Corporation. This week's webinar is on energy recovery ventilation for commercial applications. As you probably know, down in the bottom right-hand corner of the screen, there's a question chat box. Feel free to type in questions there, and I'll take a look every few minutes or so to see if we have any questions, and I'll try to address them on the fly. And if I can't for some reason, then I'll look up the answers and get back with you after the presentation. This webinar is being recorded, so you can share it with coworkers after the fact, and the recording should be posted up here later this afternoon. All right, so here we go. Energy recovery ventilation for commercial buildings. So this is kind of our agenda lineup. We're going to talk about ERV fundamentals, how ERVs work, why they're becoming more common now, and why they're going to become a lot more common real soon, what types of technologies are out there to do energy recovery with, and what are the standards and codes dictating to us. And then if we have time, we'll also look at some software tools used to calculate energy savings. Either way, I'll show you the output of some tools, but I don't know if we'll have time to actually run the tools. All right? So first off, ERVs. Pretty basic here. An ERV is an energy recovery ventilator. It can also stand for enthalpy recovery ventilator, depending on who you're talking to. Today we're using it in the broad sense of the term, so energy recovery ventilator. The biggest thing happening on these type of systems, we have to find out how much outside air we're talking about. If you got a system that only has 300-400 CFM of outside air, an ERV is not going to be all that exciting of a payback scenario. However, if you've got 30,000 CFM of outside air, it's going to be an absolute no-brainer. So we got to figure out in between all those ranges, when does it make sense and when does it not make sense from both a economic standpoint and an energy consumption standpoint. So that's really what we're going to focus on quite a bit today. So how much outside air are you talking about on your project? That's the first question anyone's going to ask you when you talk about an ERV. So the goal of this ERV is basically to take the exhaust air that we were going to throw out of the building and just totally get rid of it, and instead recover the energy from that exhaust air. So not the actual air molecules or anything like that, just the energy in the air. Energy in our case today is going to be heating energy, cooling energy, humidification energy, and dehumidification energy. So we're going to grab that energy out of the exhaust air and transfer that energy over to the outside ventilation air that's coming in to preheat it, pre-cool it, pre-humidify it, or pre-dehumidify it, or some combination thereof. So here it gives you an example down here on the left side here. And I'll see if I can use my my John Madden Telestrator tools here to kind of highlight things as we're talking here. See if this works very well. All right, so on the bottom left side, we're doing the summer conditions right now. In this example, we have outdoor air conditions of 95-degree dry bulb, 78-degree wet bulb. So this is a pretty hot, humid day, pretty much an extreme day for most of the climates that you guys are in, which is the Midwest for most of the guys on this call. But on our exhaust air, we are about to throw away 75-degree, 63-degree wet bulb air. Just totally throw it out the exhaust air. So instead, we're going to grab the energy from that return exhaust air and transfer it over the wheel in this example. There's other types, and we'll explain that later. Transfer it over this wheel to the outside air to preheat it, or excuse me, pre-cool it and pre-dehumidify it. So we went from 95-degree dry bulb down to 81-degree dry bulb, from 78 wet bulb down to 68 wet bulb. So that basically means this air that's going to be over here delivered to our normal HVAC equipment, probably a rooftop unit or something like that, that air on a 95-degree day, that rooftop's going to think it's 81 degrees outside. He'll have no idea that it's 95. Exact same thing on the wet bulb side. We're dropping 10 degrees of wet bulb here. So pre-cooled, pre-dehumidified. That's a fantastic story, and we'll talk later on about why that's important for comfort reasons. And it does save us some energy, but the real energy saving story is in the winter conditions. So over on the right-hand side over here, we have an example for wintertime. And the example we're looking at here is a 7-degree day outside. So not even the worst day that we'd have here in the Midwest, but just a regular cold day. And I have 72-degree return air that I was going to throw out and just get rid of it. Instead, I'll recover his energy and increase that 7-degree outside air up to 53-degree dry bulb. So I'm getting whatever that is, 46 degrees of heat rise for free, for the price of spinning this wheel. So my HVAC equipment over here, he thinks it's 53 degrees outside when it's really 7 degrees outside. That's how much preheating we did for the price of spinning a wheel. Additionally, we reclaimed some of this moisture that was going to be exhausted out, and we've increased the wet bulb of the outside air from 6-degree wet bulb up to 40-degree wet bulb. So it's a free heat or near free heat and near-free humidification system. That's kind of really what we're talking about here. It looks like we had a question that did pop up. Someone that works in a humid climate, high latent load in the summer and the cool shoulder months. What dehumidifying ERVs can you recommend, particularly for zoned multi-unit commercial buildings? All right, so in your case with the humid climate, even though most of the guys in this call are Midwest, you're in a humid climate, which is fine. Even in the Midwest, we have very high humid days for 3-4 months out of the year. So the type of type of ERVs that we're going to be using are going to be the ERV type, enthalpy recovery ventilators. We are not going to be using HRVs. And I'll kind of explain the difference between those two in a minute. But we want this scenario that I just described here on the bottom left. I want to take that dry exhaust air and use it to pre-dehumidify my outside air coming in. So the more regular that my air outside is humid than indoor, the more beneficial that's going to become. All right, so in order to use any type of ERV, we got to get these two air streams, the exhaust air and the outside air, near one another. If they're not near one another, it's going to be very hard to exchange the energy. So this is what a lot of buildings look like. I may have an HVAC unit, in this case a rooftop unit, and then unrelated to that I got some centralized exhaust fans or bathroom exhaust fans or something like that. I need to find a way to duct that air over to the HVAC unit. There's going to be several ways we can do that. Right here it just happens to be one of those ways. I could basically put these two pieces of equipment together, either one giant unit with both pieces built into it, or like we're showing here, two units side by side, and I got some common ductwork between the two of them. We'll explain more about different ways to do that as we go through here with lots of actual real photos of installations. We got to get the exhaust air near the outside air. That's what we got to do. In addition to the energy savings, there's going to be some other benefits of these systems. One is going to be reduced load on the compressors. I'm going to have smaller compressors on my HVAC equipment, hence a lower peak demand load. So not only will there be energy savings, there could actually be less demand savings if your particular utility charges you demand charges. We're going to get savings both in the summertime and the wintertime operation. So this is not just one season or the other. This works in both seasons. Our dehumidification control is going to be significantly enhanced, whether you are in a high humid area or whether you're just in a regular Midwestern climate where it's humid only some parts of the year. And the payback on these systems is going to be very large. I'm going to show you some examples here in a minute. But normal paybacks, if you're already replacing HVAC equipment anyway and you're considering adding an ERV, those paybacks are probably going to be in the 1 to 2 year time frame in most cases. So here's an example of some paybacks that we've calculated. Just a quick background on this particular chart. We use this in the Midwest as a kind of just a cheat sheet, as an initial starting point, and then we'll calculate examples specifically when real projects come up. But this particular cheat sheet is assuming that in the wintertime I have minus 10 degree outside air on a design day, and it's assuming I have 95, 76 for my summer design conditions. And it's assuming 10 cents a kilowatt hour and $1 a therm in this particular example. We can obviously do it based on whatever utility price we really have. So if I look at some examples here, for example, a 1500 CFM system, my cooling reduction is going to be almost 4 tons. That means when I put the new rooftop or air handler in this building and I decide to use an ERV with it, my HVAC equipment is going to be 4 tons smaller than whatever it used to be. I'm going to reduce that load on a peak day by 4 tons. On the heating side, I'm going to reduce it by 120,000 BTUs. So I'm going to buy a smaller gas heating section or smaller electric heater or whatever it's going to be. On that design day when it's 95, 76 outside in the summertime, after the air leaves my ERV wheel, it's going to be 80, 67. That's usually what we target in our office as a design condition leaving the wheel on a design day. The reason we pick 80, 67, and we can certainly design wheels and other ERV types that get us better than 80, 67, so lower. But we pick 80, 67 because it's a very nice compromise of first cost of the ERV and productivity of the ERV, efficiency if you will. 80, 67 is the temperature at which air handlers and rooftops and fan coils are designed at for incoming air to the evaporator coil. So if I get it down to 80, 67, it's almost as if there is no outside air load at all. I basically have reduced the outside air to match what a typical return was supposed to be for that equipment anyway. So it's like having no outside air. I basically neutralized it. On this same example, on a minus 10 degree day, I'm going to be bringing in 50 degrees discharge off the wheel. So this example, I got a 60 degree rise off of this particular wheel, which is substantial when you think about it. I'm getting 60 degrees of free heat. Now, in some cases, 50-degree discharge may be enough to avoid my unit from even kicking heat on. In other cases, I'm going to have to put the heat on, but in much smaller cycles. A question came in from Michael about hotel/motel applications with shafts serving multiple exhaust ventilation. Those systems are not very well suited to ERVs, not just high-rise hotels, but also condominiums and apartment buildings that are multi-story with individual exhaust fans. The problem with anything with individual exhaust fans is that I can't get all the exhaust air near the incoming air. If I have a centralized exhaust fan in those buildings, then it's much more feasible, and it's very doable in those cases. The payback on that example I was just talking about is 1.6 years. Now, on this particular chart, all the payback calculations are assuming, this is a rooftop chart, but we do charts like this for other systems as well. This is assuming the rooftop is going to be replaced anyway, so you're buying a new rooftop, but instead you're going to buy a smaller rooftop, in this case 4 tons smaller, and put an ERV on the side of it and work those two pieces of equipment in conjunction with one another. So these paybacks are taking a credit for the fact that I'm buying a smaller rooftop, taking a credit for the summer and winter energy savings, and I'm taking a penalty for the pressure drop of the wheel and a penalty for spinning the wheel with a motor. So all in all, that thing's going to save me $1,400 a year, payback of 1.6 years. I don't know if you saw there too, the return on investment is 63%. So return on investment, if you're not familiar with that kind of terminology, and hopefully most of you are, that basically means if you have somewhere to invest your money that gets you better than 63% investment return, you should do that. So if you got a really hot stock pick, great, go ahead and do it. Otherwise, spend your money on energy efficiency in this case. Another example here we'll pick out from the list, a much larger unit, 12,000 CFM of outside air. So this is a very large unit, obviously. In this case, we can reduce the cooling tonnage by 31 tons. That means I'm going to buy an air handler or a rooftop unit that is 31 tons smaller than I otherwise would have bought. And I got almost, in this case, 1 million BTUs smaller on the heating side. Still getting 80-67, still getting basically a 60, or in this case 58-degree rise over the wheel in the heating season. My payback is 0.1 years. That basically means this thing pays itself back in a month. And just to be fair, the reason that some of these are really good, like 0.1 years, 0.3, 0.4, like I said, we're downsizing the rooftop and taking a credit for that. Well, if I downsize your rooftop by 31 tons, I'm probably in a much smaller chassis of rooftop in the, I don't know the best way to say it, in the commodity version of a rooftop as opposed to the larger, more custom type rooftop. So I'm going from, whatever, a 50-some ton rooftop down into something that's in the 20s, and it's more of a commodity and hence significantly cheaper. So that's kind of why that works that way. In this case, $11,000 savings. Paige writes in if these economic analyses included labor or just equipment cost. This included both. So this was everything in all. This is cost. We worked with contractors to develop this because we're a distributor. We worked with a couple of contractors to develop this. This is the costs of buying the cost difference of buying a new, smaller rooftop, right? Which that's a credit in that case instead of buying the big rooftop. The cost penalty of buying the ERV, any equipment used to link those two together, and the installation labor associated with installing the extra ERV. The installation for installing the rooftop was not in there because you're already replacing the rooftop. So basically, it's just the incremental costs of I was going to put in, for example, a 50-ton rooftop and replace it. Now instead, I'm going to buy a 30-ton rooftop and an ERV, and I'm going to install it, a little bit more work because there's more work to be done, electrical and so forth. So only the incremental cost difference of the labor and the equipment. So hopefully that answers the question, Paige. All right, so different types of ERVs that we can use. There are 4 main major types, and there are some other ones out there that are much more niche, like liquid desiccant systems and things like that. But the 4 main types we'll talk about today are wheels, fixed plate cores, heat pipes, and hydronic runaround loops. So I'll show you examples of all of those and kind of discuss when to use one over the other, pros and cons, things like that. And I already mentioned ERV versus HRV. HRV is heat recovery ventilator. It only does sensible energy recovery, no latent, so it does no humidification, no dehumidification, just heat and cool. ERV does all 4, heat, cool, dehum, and humidification. All right, so first, why are these things becoming more common now? We've seen a significant spike in ERV sales over the past 7-8 years, and we're continuing to see that trend rising significantly faster than any of our other types of equipment sales. with exception for perhaps variable refrigerant flow systems, which are also on a very fast click right now. This is why we focus a lot on rooftops. We do ERVs at our office for air handlers and other equipment as well, but rooftops is a huge focus for us, and that's because rooftops are the giant piece of the market for both just regular systems as well as ERVs. So on the left there is ERVs by dollar, and on the right is ERVs by quantity, and that purplish, magenta-ish color is DX packaged systems, so basically rooftop units. As you can see, whether it's number of units or money, rooftop units are more than 50% of the types of equipment that we put into buildings. There are also some standalone ERVs that get installed, and there are some that are integrated into air handlers. But bolting a ERV to the side of a rooftop unit is by far the most common application. The main drivers on why these are becoming more popular are because of the standards that have changed over the past decade, and these standards feed into the codes. So there's two main standards at play. One is ASHRAE Standard 62.1, which is the commercial ventilation standard. Amongst other things, this standard specifies how much outside air needs to be brought into a commercial building, and there's tables in there that dictate how much air is brought in for different types of buildings. So for example, an office building, you have to bring in 5 CFM per person plus 0.06 CFM per square foot. Schools have a similar chart, but it's much higher outside air. Some spaces have less, but there's a chart for each type of building scenario and how much outside air you have to bring in. And overall, those rates are higher than they used to be compared to the buildings that we're retrofitting. So that ventilation rate is about 50 to 75% higher than what it was when these buildings were built between World War II and, say, 1990. So the buildings you're retrofitting need more outside air now when you rehab them. The other main standard at play is ASHRAE Standard 90.1. This is the standard that sets forth our energy conservation rules for the country. Both of these standards feed into the applicable international codes, and those codes get adopted by local municipalities. So for example, in Illinois where I'm at, we are using the International Energy Conservation Code 2012 version, and it is based on ASHRAE Standard 90.1 2010. And as far as ERVs are concerned, the language is identical. So there shows you our historic ventilation rates over time. And as I said, anything built after World War II was probably designed with 10 CFM per person in mind, maybe 5, maybe 15, but pretty much anything between World War II and the end of the 1990s was designed with 10 or 15 CFM per person. And nowadays, most of the codes are going to average out to be around 17 CFM per person for an office building type example. So we need more outside air than we used to when we retrofit these buildings. On the energy code side, the old code for Illinois and the code for almost every state in the Midwest and most of the country is 90.1 2007, also International Energy Conservation Code 2009. Those are identical, and they would state that if you have a system that is 5,000 CFM of airflow for the total airflow of the supply fan, and 70% of that is made up of outside air, you are required by law in most cases to install an ERV. There's exceptions for places that are not, heated and cooled and things like that, but for the most part, 5,000 CFM, 70% outside air or more, you got to put an ERV in. Well, most buildings don't have 70% outside air. That's a pretty rare scenario, and it pretty much limits it to dedicated outside air systems. However, the new code, 90.1 2012, or International Energy Conservation Code 2012, is a little bit different, and it's a tiered system, and we have this system in effect in Illinois, it's in effect in Maryland, statewide, and then it's also in effect in some select municipalities around the country. But this is something that gets adopted nationwide. We just happen to be the first ones over here in Illinois to do it. The country has different weather zones that we're divided into. This is not just for this standard, but for many other ASHRAE standards. So if you are in Chicago, for example, where I am near right now, I am in climate zone 5, this green climate zone, and I am to the right of the magical moist humidification line here. So if you're on the right side of that line, you're in the A zone. So I'm climate zone 5A in Chicago. Those of you guys up in Wisconsin, you're 6A. There was somebody that said that they were from, a humid climate, so they're probably down here in Florida or Alabama or something like that. So you're probably 1, 2, or 3A. All right, so looking at that, that's our map. So kind of figure out where you're at. If you're on the left hand side, you're in the B climate zone. over there, and then there's a marine one over on the far west coast. So this is what the table looks like based on those particular climate zones. So I said we're in climate zone 5A. So it used to be 70% outside air, 5,000 CFM. Now 70% outside air is 1,000 CFM, right? And there's also a tiering system for airflows less than that, outside air percents less than that, all the way down to 30% outside air, 5,500 CFM. Well, 70% was not very common. 30% is much more common. It probably won't include some of your typical maybe office buildings, but things that are densely occupied, like a school, for example, that has a very high ventilation rate and a high density of people, probably will fall into some of those ranges, that 30-40% range. So some of those buildings may be required by law to put an ERV in. Other spaces, like your typical office, probably less than 30%. So in those cases, you don't have to put an ERV in. But I think when you're done looking at this today, you're going to see that it still makes some economic sense to do so. There are other standards in play that I'm not going to go through today, but there's standard 189.1, which is an ASHRAE standard, and International Green Construction Code, and those two are similar to each other, and they are for places that want to adopt codes that are more strict even. And then they have tiers that are even further below that, all the way down to 10% outside air. I point this out even though most municipalities do not adopt these standards. I point it out because what goes into these standards now usually ends up going into the regular standards 3 to 6 years down the road. So this is something, kind of a glimpse of what the future is always going to be when you look at these standards. If you're doing LEED projects, there's also benefits for ERVs there. Obviously, the energy reduction is a benefit, and that helps you with EA Credit 1. Depending on how much you can reduce the energy consumption, you can get additional credits for that. If you choose to do the increased ventilation credit, EA Credit 2, or excuse me, EQ Credit 2, I'm not a fan of increasing the ventilation. In fact, I'm a fan of decreasing it below the code required amount with using CO2 sensors. But if you want to do that increased ventilation and increase your outside air by 30%, that's fine. There's health benefits perhaps to doing that. But when you choose to do that, you're going to use a lot more energy. So the ERV is a way to offset that energy and make it kind of an energy neutral penalty. You can also, depending on the type of ERV you get, some of them may have built-in airflow monitoring stations, and some of them can be modulated based on CO2 sensors. Either one of those will help you with EQ Credit 1, which is recording data from outdoor air delivery. So you can do that with airflow or CO2 sensors depending on population density. And there's also benefits for dehumidification control that can help you achieve ASHRAE Standard 55, which is EQ Credit 7.1. So there's some benefits there on the LEED side of the equation. Let me just pop open real quick this question box and see if anybody has typed anything. Let's see. Tony types in, what is the ventilation standard for data centers? Tony, I don't know the answer to that question, but just based on my observations, I've never seen a data center bring in any ventilation air in. And the fact that there's usually only 2 or 3 people in a very large data center, where the server racks are, my guess is the ventilation rate is 0 or very near 0. The leakage of the dampers probably covers you on that. So an ERV is not going to be something that's applicable to a data center. Additionally, you're trying not to save that heat in a data center. You want it to go away. So you're probably not going to see ERVs in data center applications. Hopefully that helps answer the question a little bit. All right, so what types of buildings do we want to put this in? I just said data centers probably aren't a great candidate. Not that you couldn't do it, it's just not the best candidate. The best candidates are the ones that have very high ventilation rates, which are ones that have typically lots of people. So schools are great, auditoriums, movie theaters, offices, nursing homes, sometimes restaurants, depending on whether somebody chose to steal the dining room air to make up the kitchen hood. If they chose to do that, then it's not going to be a good candidate because you're not going to run grease through an ERV. Fitness centers are good candidates. Locker rooms are good candidates. So those are the typical kind of places that we often put them in. Ones that have lots of people and a fairly high density, because those ones have the highest outside air requirement, hence the faster payback of ERV technology. All right, so speaking of technologies, let's look and see if we got any questions. All right, so different types of technologies. Let's go through them kind of a little bit here. So the first thing before we talk about the major types of technologies is to understand how they're rated. Sometimes you'll hear the term efficiency, but that is not a correct term because it's not technically using much power to get the output. And if you looked at it from a pure efficiency standpoint, all the efficiency numbers would be higher than 100% because we're using waste heat recovery. So the correct term per the AHRI standards is effectiveness. So what is the effectiveness of the ERV is the proper way to term that. And this shows you how that's calculated. So I got a couple different air streams here. Going in this case, I'm showing a wheel example, right? But the example would be the same for other types of ERVs. Got outside air coming into the wheel, and that's getting turned into my supply air. I got exhaust air leaving the building, going through the wheel. That's going to go ahead and exit out, and the heat exchange is happening between these two air streams. So the question becomes, how warm, cool, humid, or dry is my return air that I was going to throw away versus how much did I actually recover, right? So if you look at the math on that, and right now we're just going to talk about temperatures and not talk about humidity for the moment to make it easier to understand. I got 95-degree air coming in. I somehow magically made that turn into 78-degree air. The best I could have done was make it 75 because I had 75 to work with. So what was the most I could have got? 20 degrees in this case. What did I really get? 17 degrees. So it ends up being 82% effective, right? So what's the difference of outside versus supply divided by outside over return? How much did I get versus how much was the absolute theoretical maximum that I could have gotten? When you throw the humidification into the discussion, instead of doing this with temperatures, you would do this with enthalpy numbers, BTUs per pound of dry air. But the math would look similar. In wintertime, it works the same way. We just kind of change the numbers around because no one likes negative numbers. But basically, what is the most I could have gotten out of this system? So return air minus outside air, what's that delta T? 60 in this case, versus what did I actually get, right, which was 48. So that's 80% effective on the winter mode operation. Syed asks if this is applicable to isolation rooms in hospitals as well as labs. The answer is going to be dependent upon the specific code that you're looking at and the type of heat exchanger you choose. So in an isolation room, you probably have to have absolutely 0% leakage, and I'm going to talk about leakage in 1 minute here. So you're going to have to choose an ERV technology that will give you guaranteed zero leakage, and you're going to have to rely on that particular governing body, so here where I'm at, Illinois Department of Health, to allow you to use ERVs, right? So you're probably going to be able to do it with a fixed plate, but probably not with a wheel. For the lab question, it's going to depend on what you are exhausting from the building. If you are exhausting substances that will be harmful to the ERV heat exchanger material, then you're not going to be able to use it. But if the exhaust fumes are not harmful to the material, then you would. So in those cases, we look at them on a case-by-case basis. You tell us what's going to be in your exhaust, and then we look at that with the ERV manufacturers and their different materials to see if we can use something or not. So that's kind of how those go. Also, I want to just mention that those effectiveness rates that I was showing you how to calculate there, those are assuming that all the airflows, all the CFMs going in and out of the building are equal. Well, in many applications that's not the case, and I want to keep some buildings, like an office building or something like that, slightly positively pressurized. So I will have some more ventilation air than I have exhaust air, and that does change the equation, because if I'm exhausting less exhaust air through this wheel, I have less energy to recover from, hence I won't be quite as effective. So when you look at the effectiveness of a particular manufacturer's product, you need to look at that specific to your airflows, not just what they put in their various catalogs. So for example, in this case, if I had an, let's just say here, 80% effective product that it was cataloged that way and rated that way, right there would have been 80% where my my little pen circle is. I'll circle that. But I happen to have more ventilation air than I have exhaust air. So let's say I have 20% more ventilation than exhaust. So 0.8 is my ratio here. So my 80% effective product dropped down to be a, we'll call it, I don't know, that's probably 64% effective product. It's not a bad thing. It's just that I need to know that when I'm doing the math, when I'm sizing my HVAC equipment, that I'm not going to get 80% recovery. I'm only going to get 64 in this case. But I do have to keep some buildings positively pressurized. The best I could possibly do would be 100%, and that's only if I put the heat exchanger in the correct place, right? So if I decide to run these two airflow paths parallel to each other, oh, what happened to my mouse there? Sorry about that. If I run these parallel to each other, so I got 10 degrees and 70 degrees in this case, well, even if these guys end up being the exact same temperature when all was said and done, they basically would average out to be even between them, so 40 degrees. And if it wasn't 40 degrees, then if I run the ductwork another mile, it'll be 40 degrees. And if it's still not 40, run it another mile. Theoretically, the best I could ever do is get them to be the same. I can never get the outside air to be warmer than the exhaust air, right? On the flip side, if I run these things in counterflow arrangement, so I got one airstream going to the left in this drawing, one going to the right in this drawing. If I do it that way, then I can actually get, theoretically, 100% recovery. So that 10 degrees will eventually become 70. That 70 degrees going the other way will eventually become 10. And if it doesn't, just imagine the ductwork being 1 mile longer. And if that doesn't get you there, imagine it being 8 miles longer. Theoretically, eventually to be 100%. But I'm not going to run the ductwork for 8 miles, so I'm not going to get quite 100%. But I can certainly get stuff up into the high 80s. The sweet spot tends to be in the mid 60s to low 70s. Sweet spot meaning most cost-effective point for the technology that I'm buying versus the recovery effectiveness that I can get. So I mentioned the term leakage earlier. There are actually two types of leakage. There is leakage on the exhaust air, accidentally cycling into the supply air. So I think that was what the question was a little bit earlier. So some of that leakage going this way, back into my supply. I want to minimize that because if this return air is, say, bathroom exhaust, I don't want a bunch of, bathroom odors making their way into my supply air. If it's just general exhaust from the building, not as much of a big deal because I was going to recycle that anyway. I also have leakage on the other side of the ERV, in this case a wheel, that's short cycling over here. There's penalties to that as well, and I'll try to illustrate both of these here. So on the exhaust air accidentally leaking to the supply air scenario, the correct AHRI term for that is exhaust air transfer ratio, or EATR, because everything has to be an acronym in our industry, obviously, or it's not real. In this particular example, we have 5,000 CFM of return air coming into the ERV, and I got 5,020 that's leaving it because 20 CFM was short cycling off the front side of the wheel and leaking through. So in this case, 0.4% leakage, which is pretty low, but pretty common. On the other side over here, the AHRI acronym is Outdoor Air Correction Factor, OACF. That's just that air that's short cycling that path over here. There's no problem with that in terms of like odors or anything like that. The problem there is energy. In this case, I'm short cycling 8%. So that means to get 5,000 CFM shoved through this wheel, I actually have to run a fan at 5,400 CFM because 400 of it's going to accidentally leak up the front of the face of the wheel and get exhausted out on accident. So I'm forced to buy a bigger fan than I wanted to, and it's going to use a little bit more energy than I had wanted it to. So obviously I want to minimize both of these numbers, but it's kind of hard to minimize both of them together. Generally when I touch one, it's going to affect the other one negatively. So in a lot of cases, we're trying to optimize the EATR, so that way no one smells the odors in the exhaust air, or if it's objectionable air, I'll have less of that. But it may mean I need to have a little bit bigger fan on the other side of the equation. Let's see. Syed asks, could the leakage be eliminated or minimized by pressurization? Absolutely, Syed, and you're leading me right into the next set of slides here. Where I choose to position the fans relative to the heat exchanger, the ERV wheel in this case, has a big difference on how much leakage I'm going to have. So if you look at this here, if I put this fan in the return position over here, his job is to push air this way against this wheel. Well, if I'm pushing air into the wheel, some of it's probably going to leak down the face of this wheel through this little crack. We have little, airflow blockers in there, but it's basically the same as weather stripping on the bottom of your door. It's slightly higher tech than that. So some air is going to leak that way. And if I got this fan pushing against the wheel, some of it's going to leak down. Then down here on the bottom, the supply fan's pulling the air that way. So I got air pushing and air pulling at the same time, and that's pretty much going to guarantee me a fairly high leakage rate. However, where's my mouse? If I move that return fan over to the exhaust position, if you will, now that guy's pulling through the wheel instead of pushing against it. So he's actually kind of pulling air up this way a little bit, even though this guy's kind of pulling down. So that's going to minimize the amount of leakage. Instead of this guy pushing down and that guy pulling down, now they're both kind of pulling their opposite ways. So by having these fans positioned in this arrangement here, it's going to minimize the leakage on this side of the wheel, which is the one that I'm concerned with for odor transfer and things like that. The other thing I can do would be to add a purge angle, a purge section to this. This would be applicable to an ERV wheel style. What a purge section is, or an angle, is basically a piece of sheet metal that's angled right here that blocks off the first piece of my wheel pie, if you will, so these little pie pieces. he kind of blocks off that first piece and takes some of that ventilation air coming in and hits that angled piece of sheet metal, which forces air to go up because it's on an angle going that way. That forces more of my leakage to happen in this direction versus going downward. So I'm forcing some leakage upward to prevent downward leakage, and that will help me get that thing down to a very low leakage, very times often down to 0% even. So kind of looking at it in summary, you don't want to have the fan in the return position ever. That's going to be the worst thing for leakage. So that return fan needs to always be moved over to the exhaust position. That'll minimize the leakage on this side of the wheels, right? Then the other fan, I can kind of choose where I'm gonna put it. I can put it on the outside air pushing in, which really minimizes the leakage on this side, or I could have it on the supply fan as a draw-through side, and I might have to add a purge to get it down to the number I want. The important thing to note here is that you put this guy in the exhaust position on that side of the wheel. That's a critical piece. In terms of recovering moisture from these systems, we can't just use a piece of a metal wheel spinning it through the two airstreams. I got to have something that can absorb moisture, and metal's not going to do that for me. So typically the ones that do moisture transfer, so enthalpy recovery ventilators, ERVs, they're going to have some kind of desiccant impregnated into the plastic wheel itself. So metal wheels will very likely only do sensible energy. Plastic wheels will help me do latent energy if I impregnate it with a desiccant material. This desiccant is permanently built into the wheel. It does not have to be regenerated. It can be made of different materials. The most common one is a silica gel. This is the same stuff you find in the packets with electronics and leather shoe boxes. The one that says do not eat silica gel, that's the same thing that we're putting on these wheels. The reason they put it in your electronics and your shoe boxes is because we want to keep that moisture neutral in those boxes as we ship them around the country. And what a desiccant does is it absorbs moisture or releases moisture, depending on which moisture, which is higher, the higher moisture stream. So the wheels can do the same thing. As it goes through one airstream, if that's the higher moisture stream, it's going to absorb the moisture. When it spins to the other airstream, it's going to release the moisture. So this will work automatically in both directions, summer and winter, saving me moisture in the winter and preventing me from getting outside moisture in the summertime. The question is, can we use the same in AHU in built double-decker type? I will show you some pictures of that in a second. But yes, your fan positioning guidelines should be the same. You want that return exhaust fan to be in the exhaust fan position specifically. And I'll show you some examples of that shortly. Here's just some examples of different types of desiccants. The two major ones that are used in ERV technology are silica gel and molecular sieves. And you can see they have different curves associated with them with their absorption power related to the relative humidity of the return air or the outside air. And a molecular sieve gives you a fairly even profile across, whereas a silica gel has a much steeper curve to it. And the more humid it is or the more drier it is, more drier if that's a phrase, the more dry it is, it'll absorb more or release more moisture. So a silica gel does a really good job over a wide range of humidity conditions, which is what most climates will very likely have. Because we are reclaiming moisture, and that moisture is going to be transferred to outside air, and that outside air could be below freezing, we do have the potential for frosting up the wheel. It's very simple to predict when we're going to have a frost condition. If you're familiar with the psych chart, and hopefully most of you are, and real quick orientation on the psych chart. Down in the bottom here we have all of our dry bulb temperatures, and as you go to the right, the temperatures get warmer and warmer and warmer. Up the left-hand side we have our moisture content, and the higher you go, the more moisture there is. And then we have all of our humidity curves, so 60%, 70, 80, 90, and then that top one where the chart stops, that's the 100% curve, the saturation curve. So if I'm at that point, I can hold no more moisture in the air. So the way to figure out if I am going to have a frost condition, I plot my outside air conditions on the psych chart and my return exhaust air conditions on the psych chart. Right, so there's my outside condition in this case, -5 degrees. And if I plot my indoor condition, in this example, 75-degree dry bulb at 45% relative humidity, if I draw a straight line between the two of them, and that line intersects the saturation curve, then I'm going to have a condensation issue happen. And if that condensation issue happens when I am below 32 degrees, then that condensation will begin to turn to frost. And obviously the more frost I have on the wheel, the less heat transfer it does, and the harder it is for me to blow air through it, etc., and I will need to defrost that wheel. If I am below that saturation curve and I never touch it, then I do not need a defrost solution. So there's several ways to solve this frosting condition. Let's say this was our actual selection here, -5 degree design day on a 75-45% indoor condition. Boom, I'm going to have this this frosting issue occur at 26 degrees. This is relatively high because I have chosen a 45% relative humidity in this example. Most buildings in the wintertime are not going to have 45%. They're probably going to have 20%, which is going to be, you know, way down here on the chart, right? So if I draw my straight line there, I'm probably not going to hit it till I get down to like 0 degrees or so. But let's just say we're here on this particular example. There's a couple ways for me to solve this problem. I need to get this line to not intersect the saturation curve. So I could heat the outside air from -5 to, say, 0 degrees, which is not very much energy to do that, and then redraw my line. And I'm not drawing it very straight with this little pen, but redraw my line there, and now if I don't hit the curve, I'm good. I only need to add a little bit of heat to do that, right? So that's heating my outside air coming in. However, that outside air I heated coming in, if I have a 70% effective wheel, 70% of that's going to get transferred over to the exhaust air and thrown away. So I probably don't want to heat the outside air coming in. I probably want to heat the return air leaving the building, which sounds really weird, but that return air, if I heat it, it's actually going to go into the wheel, and I'm going to recover 70% of it there and save that energy. So if I actually heat that air, so from, say, 75 to 85 or something like that, then redrew my line. Here, let's see if we can clear that a little bit. Oops. So if I heat that to 80 degrees, the line moves over to here. There's my new dot. Now if I draw the line, it's not very straight here, but you can get the idea. It's hard to do with the mouse. I will be able to avoid hitting that saturation curve. So it's easier to heat the return air than it is to heat the outside air coming in, although it will be counterintuitive in your thinking. Some products do better in frostier climates, if you will, than others. An enthalpy wheel is going to do a very good job. An enthalpy wheel is easier to defrost than a fixed plate core. And enthalpy products are going to probably do better than sensible only products as far as defrost is concerned. So that's just kind of a chart to kind of get you thinking about that. Here's a chart with specific examples for you. Whether I frost or not is a function of the, like I said, the indoor moisture content and the outdoor temperature. So this chart we have indoor humidity on the left, indoor temperature on the top, and then in the box it tells you what outside air temperature the frosting situation will happen. So if I have 30% outside air at 72 degrees indoor air, that means when I have -2 degree outside air, I'm going to have a frost condition, right? If my air was warmer inside, say 80 degrees, which you probably would not, that's a bad example, you wouldn't design that. Say 75 degree indoor temperature and 30% humidity, -1. If it's more humid, say I got like a fitness room, right? So maybe it's 50% humidity in the summertime at, say, 70 degrees maybe for a fitness room. So that means at 12 degrees outside, I'm going to have a frost concern. So the higher the humidity is in the space, the higher the outside air temperature I'm going to have a frost issue with. So think of high humidity spaces on whether you need to do something. So that's going to be locker rooms that have showers, fitness workout rooms perhaps, and things like that. You're probably not going to have much issue with offices and schools and those kind of things. Like I said, you can use a preheater to solve this problem. On built-up air handlers, you could use speed control of the ERV wheel to reduce the frost issue. You can use what we do a lot of times on regular systems. So if I have an office building and I do the math and it's not going to have a frost condition until I get to like -5, I can look at that and say, well, how often do I get to -5? Like almost never, like 10 hours a year. So in those cases, what I'm going to do for 10 hours a year, instead of putting in electric heaters and having to power them and all that, I'm going to put in a pressure sensor over the wheel. If the pressure builds up across the wheel because I have frost, what I'm going to do is temporarily shut the outside air intake path, turn off the fan and close the damper, but I'm going to continue to spin the wheel, and I'm going to continue to run the exhaust air. And I'm going to use that exhaust air for the next 3, 4, 5 minutes to thaw off my wheel, and then I'll start bringing outside air in again. And then if I get another frost condition a half an hour from now, I'll do the same thing. The ventilation standards typically allow me to have that little bit of intermittentness to them, basically shutting off my airflow, my outside airflow for a few minutes at a time to do that defrost cycle, especially when it's only going to happen on very isolated hours of the year. All right, let me see if we got any questions. Looks like we're doing good on questions. If you do have questions, type them in the bottom right-hand corner, and I'll try to answer them. And then we'll just keep chugging along here. Whether it's an ERV wheel like we had on these examples, or whether it's a fixed plate or any other type of ERV wheel, we actually need to filter both air streams. It's probably obvious to you that we need to filter the outside air, right, because you're used to doing that on all equipment. But we also need to filter the exhaust air because there's another airflow path. And if the air leaving the building has debris and dirt and whatever in it, like it probably will, or whatever, perfumes from people and stuff like that, we don't want that getting on the ERV wheel because it's going to reduce our heat transferability. So we need to filter both air streams, the exhaust air and the outside air, before it gets to the wheel. Now I'm probably going to have to change the outside air filter more frequently because I'm going to have more debris, but I still have to have that exhaust air filter, and I still have to change that regularly. All right, this is one of my favorite charts in all of HVAC, and I use it in lots of different classes, training classes, because it does help illustrate all the bad things that could go wrong, and pretty much there's always bad things going wrong. So on the bottom of this chart, we have indoor relative humidity from 10 to 100%, right? And on the left side, we have all the bad things that might happen in my building that could be influenced by the moisture in the building. So obviously, a lot of people probably think, when it's pretty high humidity, say above 70% in the building, we know we're going to have, mold issues. People probably realize that, and that's a pretty common one. But we also have certain types of bacteria and viruses that will thrive when it's more moist. Dust mites thrive when it's more moist, and things like that. On the opposite side, if it's too dry in the building, most of you probably think in those cases, you think, dry noses, you think allergy type things, you think wood furnishings cracking, wood floors having a problem. You definitely think static electricity when you touch the doorknobs. You probably know that bacteria and viruses thrive when it's dry out. But if you look at the middle, where it's ideal, say 30 to 60%, all the bad things are minimized. So we want to kind of keep it in that range. ASHRAE Standard 62 has a upper humidity limit maximum of 60%, so you definitely want to design it to be 60% or less in a space. There is no lower limit in the current ASHRAE standards, but just based on this chart here, I think you can see if you keep it above 30%, maybe even 40%, you're probably in good shape. We'll say 30%. That's a pretty common one. Unfortunately, here's what happens on a lot of systems. So this is my typical, DX system, like a packaged rooftop or something like that. I designed it for 100% occupancy. I guess my green color is probably not going to work great here. I designed it for 100% occupancy, and I designed it for my design conditions, say 95-degree dry bulb, 76 wet bulb. When it's performing at those conditions, this example, 15,000 CFM, I'm getting 53, 54-degree dew point off the coil, which is fantastic. That helps me get an awesome 48% relative humidity while maintaining my thermostat at 75-degree dry bulb. Everything's perfect. Everything's awesome. However, in most cases, I don't have design occupancy, nor is it a design day outside. So if I look over on the part load condition over here, this example saying if I got 20% occupancy, or if I only got 80 degrees, 71 outdoor air conditions, I'm not going to be able to run the system continuously, and it's going to cycle on and off with a DX system, unless I were to get, variable speed compressors and digital scrolls or chill water valves or things like that. But your normal, 1, 2, 3 stage DX system, this is what's going to happen. It's going to cycle on and off. And it's going to cause me to have a lower average coil dew point. When it's running, great, I'll get a low dew point off the coil. But then it's going to be off for a while, and I'm going to have 70, 80 degrees off the coil. So I'm going to get an average dew point that's fairly high, which doesn't have the ability to absorb very moisture. So even though my thermostat is perfectly happy and says 75 degrees on the wall, awesome job, Ryan, you did so great for me. Oh, unfortunately, it's 71% humidity in there in that case. This happens all the time, especially on packaged rooftops, especially if they're one circuit, one stage. But even when you have 2 stages, this is still going to happen. It just won't be quite as extreme. So most of your DX systems, unless they have modulating compressors, they're going to have this problem where it's hard for me to control humidity when it's not a design day. The ERV is going to help me with that substantially. This chart here, once again, is our same psych chart. And this red bubble design is designed for what I designed most DX package systems for outdoor air conditions. So this example down here, 0 degrees outside on the low end, 95 on the high end, got high humidity here, low humidity down here, right? So I'm designing everything in that red bubble. Well, if the ERV, if his job is to preheat, his job is to pre-cool, his job is to pre-dehumidify, or his job is to pre-humidify, now I'm not concerned about the red bubble anymore. Now I'm concerned about the blue bubble. That makes it a lot easier for me to select and design the DX system to meet the conditions that I'm going to see. Because he's never going to see 0 degrees ever. He's never going to see 95 degrees ever. He's never going to see 70% humidity ever. So he's never going to have these extreme conditions. So he's much easier to appropriately size, and he's much easier to control if he doesn't have to handle that wide range. So kind of the way we tell people to think about it is your ERV is really your first stage. In this example, for humidity, is my first stage of cooling, and it's going to do a good job of me cooling my outside air and dehumidifying it. Then my compressor really becomes my second stage, and then my other compressor becomes my third stage. So I got more stages of control, so more degrees of accuracy in terms of my control sequence, and I'm going to do a much better job of dehumidifying. If you don't want to believe me, ASHRAE actually commissioned a study to figure out which types of systems throughout the country do the best job of dehumidifying, and they picked sample cities all around in both extreme humid climates like Miami and Houston, and then mildly humid climates like Chicago and New York City. And they analyzed 17 different types of systems that are designed to help with dehumidification, and 2 systems came out on top. One was a DX basic system, which is a rooftop or split system combined with an ERV. The other one was dual path ERVs, which is really more for custom air handlers. Those are the 2 that seem to shine over and over again in most climates, in most situations, in terms of lower energy cost, lowest life cycle cost, and being able to dehumidify for us. So that beat out things like reheat, hot gas reheat. It even beat out demand control ventilation, which is also a very good helper and inexpensive and can be used in combination with these guys. It beat out desiccant reheat. So this is kind of your ASHRAE answer to that. What do I do to dehumidify my outside air question? I'm not saying you don't do those other things, but if you're only going to do one thing, probably do the ERV first, especially if you got a lot of outside air. All right. Let's talk about some different types of heat exchange technologies. I kind of use a lot of wheel examples just because that's the one that I favor, but I want to explain all the technologies to you here, at least the 4 major ones. So the first one is the runaround loop, where we use hydronic coils. We put a hydronic coil in your exhaust air path, we put one in your outside air path, and then we pipe those guys together with a small circulating pump and sometimes a mixing valve, actually usually a mixing valve. And my job is to use your exhaust air to preheat or pre-cool this water in the hydronic coil, and then send that over to the outside air, reclaim that energy from the exhaust air and use it to preheat the outside air coming in. The only catch with this, and this does a really good job with systems that are where the ducts are not close to each other. So if you got like a manufacturing facility and the exhaust air is over here and then 100 yards on the other side is the supply air, chances are I'm not going to get those 2 things ducted near each other. But could I run 100 yards of pipe? Probably I could, right? That would be much more feasible. So that's where this comes into play, when exhaust air and outside air are not near each other. However, you can do absolutely no latent performance with this. This is a sensible only thing. So it can preheat and it can pre-cool, but it can do nothing in terms of dehumidification or humidification, right? I guess unless you get a hole in your coil over here and the water leaks out, then it might help you humidify. But you definitely don't want a hole in your coil, right? Another type is a heat pipe, and some of you may have heard this before. Heat pipe is similar to the runaround coil, but this one is using refrigerant-based technology, and these airstreams do have to be right next to each other. That's what one might look like in the field. So I'll have all these copper tubes going between my 2 airstreams. So here's my one airstream, here's my other airstream, right? I'll have these copper tubes going between all of them. And inside the copper tubes, it looks like this. There's no compressor in this refrigerant system. It's just a copper tube filled with refrigerant. So what happens is and here's my dividing line between my 2 airstreams, right? There's sheet metal dividing these 2 guys. So I'm going to be absorbing heat over here on this airstream, which is going to cause the refrigerant inside my pipe to boil off and evaporate. And then as it evaporates, it's going to naturally move over to the cooler side of the pipe, where it's going to condense out and give up that heat to the airstream over there. And then the refrigerant is going to condense out back to a liquid and move back along the pipe. So I got this little mini refrigeration cycle going through the pipe like this, like I'm drawing, using my 2 airstreams as my heat source and my heat sink. Works great. It's a fantastic system, but just like with the runaround coil, it's only going to be able to do sensible energy. There is no latent performance because this refrigerant never gets down to the dew point of the airstream. The next technology is fixed plate type technology. There's actually 2 flavors of this. There's an HRV, sensible only flavor, and there is a ERV, latent recovery and sensible flavor. Sometimes you'll see these ones used in little residential ERVs like I'm showing down there on the bottom. Other ones will be larger cores that might be 3 or 4 feet wide. And sometimes they'll get banked together to get me the CFM that I need overall. So it's not always just one little core like that. I can bank them together, but just you can see here with the pressure drop I'm going to be looking at on some of these systems. I don't know why it keeps doing that on the mouse. I apologize for that. These cores can go in 2 different scenarios. They can go into a counterflow arrangement where one airstream is going one way, the other one's going the 180 degrees opposite of that, or they can go into a cross-flow arrangement like I'm showing down here on the bottom. Cross-flow is definitely more common because it's easier for me to duct air here and then duct air on this path over here, whereas over here on the top one I'd have to duct it there and then separately there and separately there. So this cross-flow arrangement is the most common one that you're going to see. It's going to look like this in the real application scenario. So my return air is going to come through this way, go through the ERV, give up his energy, and energy for an ERV is going to be heat, cool, humidify, dehumidify. For an HRV it'll just be heat, cool, right? So he's going to go through that way, and then my outdoor airflow path is going to crisscross him the opposite way and pick up that energy and then go over into my supply air. So these guys are just crisscrossing all day long. One guy's giving up energy, the other guy's grabbing it. That's how those guys are going to basically work. When you look at the sensible only versions of them, it can be anywhere from 50 to mid-80s in terms of sensible. And like I said, you can also do some latent recovery if you get the ERV version of these guys. The place that we tend to use these systems most are going to be places typically where a wheel is not going to be allowed. And I'll explain some of the reasons why wheels are not allowed in certain places in a minute. But the 2 that come up frequently are facilities that are regulated by health departments, such as Illinois Department of Health. So nursing homes and hospitals may not allow you to use a wheel style because there could be some leakage on those from exhaust air to supply air, and they don't want that obviously in a medical facility. So they will require you to use a zero leakage type system, which will frequently be a core style. The other place that it comes up is toilet exhaust projects in the city of Chicago. You can use wheels in the city, but you can't use them on toilet exhaust, and I will explain that shortly since so many of you on the call are from the Chicago area. Fixed plates can be either paper, plastic, or metal. The most common sensible ones are made of metal. The most common latent recovery ones are made out of made out of paper that has a wicking effect to them. So if you've ever taken a glass of water and stuck a string in there and held it up there, you'll notice the water will wick its way up the string. That's kind of how I explain to people how these cores work. It wicks the moisture through from one airstream to the other, but is the moisture only. It does not take through any of the air molecule pollutants. One of the benefits to a fixed core style is that we don't have the moving parts that a wheel obviously has, so there's one less maintenance item. The downside to it is that it has a higher pressure drop associated than a wheel, so it takes more fan energy to use one, and it's typically more expensive than a wheel, and that's because I need more surface area because the wheel is moving, whereas the core is not moving, so I need more surface area, so hence I need a bigger cabinet, so it tends to be more expensive. So then the last type, the 4th type that's very common is the wheel type. These come in sensible or latent flavors. I showed you lots of examples of these, so I'm not going to beat it to death. But the wheel spins in a circle fashion, and I got one airflow going through, in this case, the bottom, the other airflow coming to the top, and the wheel spins between these two, grabbing energy and dumping it to the other airstream depending on the season. And there I actually showed you a good picture of what that purge angle looks like. This is a close-up zoomed of what the media looks like for the HRVs and ERVs of the wheel type. It's basically just layers and layers and layers of stacked plastic, and then if it's an ERV type, that plastic has a desiccant built into it. Recovery effectiveness can be quite high, can be up to the mid to upper 80s of total effectiveness, so that's sensible plus latent. This guy does a better job of latent recovery than any of the things we talked about. Obviously, runaround coils and heat pipes do zero latent. Fixed plates can do some latent, but not as much as an ERV would. One thing I will mention on here is that the ERV rotates at a fairly slow speed. This is not like opening up an air handler and seeing a fan rotating at like 1800 RPM or something like that. These guys are going like 30, 40 RPM, right? Really slow. So when you open it up and you see this little wheel kind of spinning around at the speed of a record, for those of you that are old enough to remember, record players, that's normal. Do not be alarmed. We need it to go fairly slow so it has time for the air to become in contact with the media and absorb and release energy. So it's going to be traveling at the speed of a record which, like a regular record used to be, like the little circle ones, the little tiny ones used to be a 45, we call them, right? That was 45 RPM is where the name came from. So kind of expect that speed. Cleaning a wheel is fairly easy. The small ones are typically a single piece, and you can take them out and do what you want with them in terms of cleaning them. The big ones are typically in a pie pattern like I'm showing you there. If they're not in a pie pattern, you should request one from your supplier that is a pie pattern because it's significantly easier to clean. You can take those pie pieces out one at a time, and you can take them, if you got a hose bib on the roof, you can rinse them out there. You can take them downstairs through the hatch and clean them. You can put them in a commercial dishwasher if you happen to have that. Cleaning them is not hard. You're doing it with typically either dish soap or any non-acidic cooling coil cleaner would work fine. So you're basically cleaning them off typically once a year, maybe once every other year once you get to know the space and know if it needs to be done more frequently than that. If you decide to put them in a place that has things that are more polluted than other places, for example, you decide to put it in a restaurant that allows smoking or something like that, or a bar or a casino with smoking, it is going to get dirty much faster, and that nicotine and tar is going to stick on there and reduce its heat transferability. So instead of cleaning them once a year, you'll probably end up cleaning them every couple months. But you got so much air in a casino that the energy savings is probably worth doing the cleaning work. If you're in a state that doesn't allow smoking, then you're probably in good shape for most scenarios. This chart here shows you side by side some of the technologies we talked about, heat pipe versus sensible plates versus ERV plates. Actually, there's two ERV plates in here just at different airflows. And then the ERV wheel style. So you can see here the blue bars are the total energy recovery, sensible and latent. So you can see how much more a wheel can do versus a typical fixed core. So that's one of the reasons, that and first cost are the reasons why we typically default to using a wheel, unless we're somewhere where the code says you can't use a wheel, then we'll default over to the core style because the energy savings is still very, very good on a core. All right, there's different ways we can connect these up to our HVAC equipment. And I realize I'm at the hour here. I'm probably going to go another 10 minutes. So those of you that can hang on with me and see the rest of this stuff, I appreciate it. If you can't, we are recording this and you could watch it later. So one way is to duct it directly to the space. I'm not a fan of this way. You would still have your air handlers and fan coils or rooftops or whatever bringing conditioned air into the space. And then the ERV would semi-condition the air and dump it into the space. And then I would be relying on the space to be where the mixing happens. So I got, on a very cold day, I might be dumping 50 degrees here, and this guy over here is doing 90, and then I'm mixing them in the space. It tends not to be the most comfortable scenario for people. So this is not the best way to do it. The better way to do it would be to duct the ERV into the fan coils. These could be regular chill water fan coils. They could be VRF fan coils, that kind of thing. So the ERV will be drawing air in here, preconditioning it as much as it can, and then ducting that over to the fan coils where the outside air path from the ERV and the return path can mix, be heated and cooled the rest of the way, and then be jointly supplied into the space. That's a much cleaner way to do it if you want to have one ERV serving multiple indoor terminal units. This works great for fan coils. It works great for zoned heat pumps, like geothermal heat pumps. It works great for VRF units, unless they're the high wall ones and there's nowhere to bring the air in. But if they're ducted or cassette type, you got a place to bring the air in through. Another way to do it is to build the ERV into the air handler. This is not something that's just for custom air handlers. You can do this on, quote-unquote regular air handlers or semi-custom if you want to call it that. Typically, you'll end up with a stacked situation like one of the gentleman's questions was earlier. And my return air path will be going through this way. My outside air path will be going through this way. And then I'll have probably a wheel in most cases spinning between these two paths. This is what that wheel will probably look like inside the unit. So one path was going that way, the other path was going this way. This guy's spinning between them, grabbing energy. We will frequently put bypass dampers in there. This one's a pretty small wheel with pretty large bypasses. Sometimes the wheel will be larger, 10 foot in diameter, for example, in which case we'll put the bypass dampers in the four corners. That's another way we might do it to save some height and so forth. And the reason we have the bypass dampers is to act as an economizer function. So if I'm bringing outside air in for free cooling, because it's an economizer day, nice mild day outside and I want cooling, there's no reason to run the ERV on an economizer day. I'm accidentally going to recover energy in the wrong direction and make my economizer less effective. So whenever the economizer damper opens, or mixed air damper opens past the minimum position to do free cooling, I will stop spinning the wheel and I'll save a little bit of energy there, and I will open up these bypass dampers to allow air to bypass the wheel, which also saves energy because I don't have to push it through the wheel, so I don't have that pressure drop with it, and allow that air to go on through. So there's 3 reasons why we do the bypass. One is so I don't accidentally recover energy in the wrong direction. One is to save the cost of spinning the wheel. One is to save the pressure drop of pushing air through the wheel. So on the economizer day, we open up the bypasses. In almost all scenarios, you will want to have these bypass dampers on your air handler system. All right, so here's a more complex air handler. Actually, not really more complex. It's just a sexier looking drawing because we can make HVAC pretty sexy here. So here's my return airflow path coming back from the space. It gets filtered because we always want to filter it before it goes through the wheel, which it goes through the wheel, gives up its energy, and then gets exhausted out the building. So my air molecules follow that path on out. My energy goes this way down the wheel. My outside air comes in, it gets filtered, it grabs that energy that my exhaust air just gave up to me, then it gets heated and cooled the rest of the way when it needs to be done that way, and then goes through my supply fan out to my space, into my VAV boxes, and whatever else I got going on. Here's an example of a heat pipe in a custom air handler. Actually, there's 2 heat pipes in this example. One heat pipe system is over here, right, and his job is to take some of that return air, grab his energy, transfer it over to my outside air that's coming in, and bring it over to my space. The second heat pipe is back over here, and his job is to grab some of that energy from the return air before it even made it to the second heat pipe, grab some of that energy and bring it over to this side airflow path of the supply air to get me some free reheat. So that's what that guy's job is in life. So we can use some of these ERV technologies not just for treating my outside air, but I can use it for some reheat after my cooling coil. So I grab some energy, some heat I should say, bring it over to this side of the airstream, and then after my air has been cooled by my cooling coil, I'm going to help reheat it back up to an acceptable temperature. So I can subcool it for dehumidification reasons and reheat it for free over here, or near free. This ERV pipe over here is for energy recovery on my outside air. Whatever energy is left, I can use that to take the guy and precondition him. Here's a similar example with a core style. So I got one ERV core over here. That guy's doing my cheap energy recovery for my outside air. But I got a second core over here that's doing my free reheat. So my return air, he's coming through here. He goes through the core, gives up his energy, and gets exhausted out. My outside air is coming the other path flow. He goes through the core and picks up the energy that my exhaust air gave up, right? Just like all the ERVs we talked about before. But then he comes on over through here and goes through a second ERV where he gives up his heat and then goes through a cooling coil to be subcooled down below the dew point so I can condense moisture out of him and dehumidify. Then he actually comes back and wraps around back to himself to pick up that heat that he had deposited earlier and then gets supplied out. So there's my free reheater, very similar to the heat pipe I just showed there before. That air comes through, gives up his heat, gets subcooled, comes back around and picks up that heat so I can heat it back up to a comfortable condition. So that's my free reheat because as most of you guys know, the energy codes don't permit me to reheat anymore these days. So doing my reheat with hot gas reheat or an ERV core is one way to do that. I could also do this with wheels. Instead of 2 cores here, I could have a wheel here and a wheel here and do the exact same kind of scenario. One for outside air conditioning, one for free reheating when I have dehumidification needs. Another way I can set these up instead of putting them in an air handler is I can put them in the duct system. This works, I don't want to say well, but this works okay for retrofit scenarios where you already have an air handler. If the exhaust air and the ventilation air are near one another, you can often add an ERV wheel to that duct system, assuming you have the available horsepower in the fans to be able to handle that. And since on average most fan systems are oversized by 60%, at least according to a Johns Hopkins study a couple years back, I probably got the fan capacity, but I still got to do the math to make sure I can do that. And I can add an ERV wheel to the duct. I could also get ERVs built into packaged rooftop type units, or kind of like a semi-custom packaged rooftop unit. So there are some examples of that. Just a regular rooftop, but we shoved an ERV wheel in there in an additional section. So I can do 100% outside air through a regular rooftop. I could also take a regular rooftop and a standalone ERV and then bolt them together. This is attractive because I don't have to buy a special rooftop like I did over here. I can buy a regular quote-unquote off-the-shelf rooftop that's a almost commodity type thing, if you will, and I can put an ERV and duct them into the other guy. There's a couple different ways to do that. I'm not going to illustrate all of them here, but here's one that's fairly common. I might have a rooftop sitting on this curb, an ERV sitting on this curb. My return air from the space is coming up on this red line. He goes through some ducting. Instead of going to the rooftop, he goes out the ERV and gives up his energy. Then my outside air comes in through the ERV, picks up that energy, goes through a duct system below the roof, and goes into my rooftop unit. So my rooftop unit doesn't know he didn't get the return air. He ended up getting outside air that was just preconditioned for him. And then my normal rooftop heating and cooling functions happen as normal. I can also do that with what we call a combo curb, a combination curb, where that same exact ducting transition I showed you here is already built into the curb. So return air comes up, goes through the ductwork inside the curb, gets exhausted out the ERV wheel and gives up his energy. Fresh air comes in, picks up the energy, goes back into the curb, goes through that side of the ductwork, and then through the rooftop, heated and cooled as normal. So this is kind of nice because I can get one single curb from the curb manufacturers that has the ducting built in. And the nice thing in our case is that our ERV supplier for this type of equipment, which is Micrometal, they also build curbs for Carrier and Bryant rooftops, which we sell. So we can get one supplier, Micrometal, to build us the ERV and the curb, and then we throw our Carrier rooftop on there with them, and it's all kind of works together. The only real negative of this scenario is I have two power connections, but that's not the end of the world. Control-wise, it's actually really easy because Micrometal also makes the economizers for Carrier. So they make us the plug accessory that we can plug into the economizer plug, and that wiring can go over to the ERV, so we can use that to track when the ERV should be running and not running and so forth. So it actually works out pretty well. This is what it looks like in the field. It's not the sexiest thing in the world, but this unit on the left side over here is my rooftop. On the right is the ERV. This particular ERV was our older style one, where it took the had the air intakes on the top. Now the one we do it now, we have air intakes on the left and on the right side over here, and nothing on the top. So it does make the ERV a little bit shorter, more along the size of the height of the rooftop. But here's that combo curb where all the duct transitions are in there. And as you can see, we do have to bring power over to this guy. And obviously we still have power over on that guy, so I do have two power connections. That's my really only drawback. But it works good for when I'm taking one rooftop off and putting a new rooftop on. I can get a smaller rooftop with an ERV and a combo curb and kind of do it all at once. And there's just different shots of what happens in different modes. That's the mode I just showed you. At nighttime, when I don't need fresh air, the ERV shuts off. Both of his fans shut off and his wheel stops spinning, and I just recirc through the rooftop unit as normal. If I have an economizer day and I chose to put an economizer on my rooftop, which is our preferred method, that economizer can open and bring outside air in, very similar to that air handler example I showed you over there, and then I can shut off the intake path fan for the ERV. I could choose to still run the exhaust path here, or I could have done the exhaust through the rooftop if I wanted to do it that way, either or. Another way we do it is we provide packaged rooftops, like this guy down in the bottom, with an ERV factory bolted to the side of it. So this works out well because now I have one piece of equipment with a single power connection and a single integrated control. There's an ERV wheel in here on an angle. I do have bypass dampers for exhaust mode, and I do have power exhaust situation here. So there's my intake, there's my exhaust. It's basically just an extended economizer hood that has an ERV wheel built into it. Then additionally, one of our suppliers, Micrometal, also makes small aftermarket ones we can put on 2 through 6 ton rooftops to bolt on there for about 500 CFM. So if I got a situation where I have an existing rooftop and they're changing the space usage and there's more outside air required, this might help me do that without having to change the equipment out. That's what it looks like inside, but it's very similar to what we just talked about in terms of the airflow paths and so forth. All right, so with that, I think we're pretty well wrapped up. That's that newer style ERV that's shorter I was talking to you about before. The reason they were able to make it shorter is that the ERV wheel is now horizontal. So that's kind of helped us out there. So one airflow path goes like this, boom. The other airflow path goes like that, boom, and it makes the unit a little bit shorter. All right, so if nobody has any further questions, I think we'll wrap it up here. The one thing I did want to mention, I don't know if I had the slide in here. I didn't. I thought I did. Maybe I hit it. Give me 1 second, and I'll unhide it and tell you the city of Chicago stuff. I must have hit it, because sometimes I do this for groups that don't care about Chicago. All right, here's what happens for normal projects that are not Chicago. International Mechanical Code and ASHRAE 62 classify the error into classes 1, 2, 3, and 4. Class 1 is just my regular, recirc air. Class 2 is like locker rooms, bathrooms, things like that. And then classes in 3 are more caustic things. For ERVs, we can typically do classes 1 and 2. And the code specifically tells me how much leakage I'm allowed to have. If I have class 2 air, such as toilet exhaust, right, I'm allowed to accidentally leak, where is it at, 10% of that toilet exhaust air into my supply air, and I will still be in compliance with the code because there's still enough air to dilute it down and not have any objectionable odors. If you don't want to do that, that's fine. You can select an ERV that has less than 10% leakage. You can select one that has 1 or even 0%. The City of Chicago is a little bit different. The City of Chicago has 2 pieces of its code that dictate what you can do with an ERV. One piece of the code here specifically says you have to have 0 communication between the outside air and the exhaust air. This was written before ASHRAE and the International Mechanical Code had any language, so they chose the term 0 communication, which all of the permit reviewers and inspectors have determined means 0% EATR, exhaust air transfer ratio. And by the way, 0.4 or 0.2 or even 0.1 is not good enough for the city. They want to see 0.0. Even if it's air you were going to recirculate on a regular project, just run it through the return air and recirculate it. As soon as you put an ERV on there, you no longer can recirculate 80% of it. You got to do 0.0. So that's one thing in the City of Chicago, and we can work with that. All of our cores would be 0%, and some of our wheel selections can be 0%, and we get AHRI certified performance data for that scenario. However, there's another piece of the code in Chicago that specifically says basically if the ERV media is in motion between the 2 airstreams and touching both airstreams, then you are not allowed to do any exhaust air from a bathroom type situation. So if I have regular recirc air, I can run it through a wheel, and there's no problem with that in the City of Chicago, and we've done several projects like that, so long as I have 0.0% exhaust air transfer ratio. As soon as I throw toilet exhaust in the mix or something like that, then I have to have not only 0.0%, but I am prohibited from using a wheel in those particular cases, and I have to use a fixed plate type design. So that's kind of the deal of what happens with the City of Chicago. All right, let me check and see if I have any final questions, and then we'll close it up. We do have one from Brad. What's the brand name for the combined unit that's shorter with the horizontal wheel? That is, the one I showed you guys there was Micrometal, this guy here. This guy's a Micrometal unit. We use a ton of these in combination with our packaged rooftops from Bryant & Carrier. They work well together kind of as a team. If you need help with that, just let me know, and I'll get you directed over to the guys in our office here that select those things all day long. We do a lot of ERVs in our office, probably, I'm guessing, around $3 million of ERVs a year. So it's quite a bit of work we do in terms of both standalone, rooftop bolt-ons, rooftop integrated, and custom and semi-custom air handlers. And then we also do residential ERVs, which is a whole other separate discussion there. So if you need help with it, let us know. We can work with you guys on that. All right, with that, I'm going to close the webinar down. I apologize for going 15 minutes over, but hopefully you found that to be of value. And this webinar recording will be posted on our website in the next couple hours. Thank you for your time, and we'll see you next week.